So, okay. Team 1, Bennett and John Martin, your time starts now.
Yeah, so we developed a two-phase landing procedure for a UAV on a moving aircraft carrier. And John Ander did most of the controllability analysis. The content, project overview, landing phases, results, controllability analysis, and conclusion. That's just a brief overview. And then here, we just have the layout of, the Simulink layout. The objective is to land the UAV on a flight deck, minimizing the difference between the downward velocities of the two vehicles, and analyze the controllability of the quadcopter if a rotor were to be damaged. And how we did this is the first phase of the landing procedure. So this is just for a general operation. We use an LQR controller, and it's tuned so that it can operate efficiently in most circumstances. And then once it gets to a set point that's at a position, I think it was 10 or 15 meters above the flight deck, it would switch to a different tuning that would minimize the difference between the downward velocities. And that is phase 2 here, where we're just trying to softly land the UAV on the flight deck. I will go to the simulation here and just show that. So we've got a close-up of the UAV on the left, and on the right, we have the UAV approaching the aircraft carrier. It's slowing down, and then once it gets above the aircraft carrier, it will switch to phase 2 and adjust all the tunings for the LQR controller. And now it's in phase 2. And you can see it starts to track the velocity pretty closely there. And eventually it will reach the flight deck. And then we did have some issues with the controllability analysis, mostly because a lot of this class and a lot of the textbook covers linear controllability, and quadcopters aren't exactly linear. There it finished up. And these are the results. You can see that the air is pretty well flat when it's in phase 2 because it's trying to match the velocities, and this is just the roll, pitch, and yaw of the quadcopter over the simulation time. And then if John Ander wants to go ahead and do the controllability.
Yeah, sure. So for the controllability, I'm going to start with the linear controllability theorem. We try to do two assumptions. The first one is that if we can control the attitude, that means we can control the position and velocity except in the vertical direction. This is basically what we were doing in the assignment with that PID controller and the LQR. For the vertical direction, we assume that the 3 other motors are over-engineered, so they can produce enough lift to at least maintain the altitude. So with these considerations, for the state vector, we're only going to use the angles and angular velocities, and the inputs, we're only going to consider the torques. For linearization, we do 2 simplifications. We assume that phi, theta, mc dot are almost equal to pq and r. And for PQ and R dot, we remove the non-linear part. Go ahead, please. However, if we want to take into account the effect of each of the motors, we have to introduce this relationship between the force produced by each of the motors and the torques. This is taken from the Quadrotor notes we used in class, and it's a linear transformation, so this is not a big issue. Go ahead, please. So we go to the controllability theorem. We are all familiar with this. We need to build the matrix C and test its rank. So in this case, after the considerations, this is the B matrix we have. What we do to simulate that one motor is down is set one of the columns to 0. Please go ahead. So we set to 0, build the C matrix, and what we get is rank N, which would mean the system is controllable. As we discussed in class, we think this is not possible. And we tested this second theorem, which is for the nonlinear system. We have to write the system as with that equations you see on your screen. The first part only depends on state variables, and the second part depends on state variables and inputs. Now, the controllability condition with this theorem is the same. C must have rank N, and f of x must be 0. However, in our case, the many derivatives in the quadrotor equations of motion depend on state variables only. So f of x will never be equal to 0, and that means we cannot apply this controllability theorem to analyze controllability in the quadrotor case. So the conclusions of this presentation, we showed a two-phase landing system for aircraft carrier operation. And we also tried to determine controllability theoretically, but at least with the methodologies we used, it was not possible. So this is all for our presentation. Thank you very much, and we will answer any questions you might have.
Awesome, great guys. So we have around 2 to 3 minutes for question answers. So please, Krishna and other judges, please go ahead and ask your questions. And I'll ask team 2 to share their slides while these guys speak. Yeah.
I have a question. My name is Shoham. Did you notice whether the uncontrollable states are at least stable or not?
Sorry, can you repeat the question?
Whether the uncontrollable states are at least stable or not?
No, they're not. As soon as you lose one of the motors,
Right.
There will be a torque produced, which will make it unstable.
Okay. Okay.
Hi, I have a question. So the system is like a nonlinear system. So did you perform any linearization? And then what's the main objective of the LQR controller?
Yes, we did perform the linearization, and that's what this was here, I believe. And it said it was controllable, but intuitively it's not. If you have a rotor go down, you're not going to be able to control every attitude. You're not going to be able to control roll, pitch, and yaw simultaneously. And
is there a particular operating point where you linearize the system?
I'll let John Ander handle that.
I don't know if your question is going more for the controllability analysis or
Okay.
questions. For the controllability,
Sure.
It's linearized close to the position at which the angles are 0. That's why we can assume that phi, theta, and c dot are almost equal to p, q, and r. For the overall operation, there's a PD controller that controls attitude, and the LQR is in charge of controlling the position of the quadcopter.
Okay.
Thank you. Question?
Anybody else have any questions? Okay. Thank you. Michael, welcome. I see you are here. I'm sending you a link for the forms that we have here.
Oh,
so.
Outstanding. Thank you, sir. Pleasure to be here.
Yeah, thanks, Michael. Okay. So let's go for team 2. Team 2 is James Faunda.
Oops. Sorry, I didn't realize I was 2.
And Team 3 is Philip Horn and Jonathan Lange. And yeah, I can see your screen.
Can you hear me all right?
Yep.
All right, cool. All right, do you want me to start whenever?
Sure, yeah, your time starts now. Yeah, sure.
Okay.
Go for it.
All right, so my name is James Faunda III, and my project was autonomous space debris avoidance. With the problem description, the reasoning behind this project is that the amount of space debris in space is not shrinking. Currently, for satellites to avoid collision with larger pieces of space debris, an engineer on the ground will have to track and determine the risk of collision. If it's high enough, then they'll have to command the satellite to maneuver out of the collision zone. And as the amount of space debris increases with each launch, this process will become exponentially more difficult. If this avoidance process was automatic, it would ease the burden of the engineer. So overall, the goal of this project is to simulate a satellite automatically maneuvering out of a possible collision with space debris. To do this, a satellite must be able to sense the debris within a surrounding area and gather it. It will then use that data to extrapolate the trajectories of the debris and predict its path. If the predicted path enters the non-tolerance range, then the satellite will determine a new orbit to track to avoid the debris. Once that debris has passed and is outside of the non-tolerance zone, the satellite will return to its original orbit. To execute this problem, I've decided to use LQR controller to successfully track a circular trajectory. The debris in the problem will be randomly generated to prevent easy maneuver scheduling and to ensure that the controller and avoidance algorithm are up to the task. The satellite will be controlled via RCS thrusters for just simple translational motion. To keep things simple, a few things have been assumed, such as unlimited fuel for the thrusters. Having a set amount of fuel would just complicate the problem. The orientation of the craft is also not a factor, so this simulation is only going to be 3 degrees of freedom. The debris will also intersect the reference trajectory to ensure avoidance actually occurs in the simulation, and no noise will be incorporated in the simulation, so the satellite will know exactly the position of the debris within a certain sensing range. And due to the 3 degrees of freedom, the Lagrangian for the system will be rather simple. Moving on to the simulation performance. As we see here with the Lagrangian derivation, it's rather simple, just kinetic energy, potential energy. And when it's evaluated and the equations of motions are derived, forces are then added in each direction to ensure control in those 3 axes. With the Simulink model, it's a similar model to previous homeworks and projects, as it uses some of the same principles such as the differentially flat reference trajectory and LQR controller. The braking criteria was added to end the simulation if the satellite falls below the surface of the Earth. First, before even debris is added, we have to make sure that the satellite will actually track a circular trajectory. As we can see in the figure on the left, the error from the satellite relative to the reference trajectory does oscillate initially from a 10-kilometer difference in the x direction, but does eventually stabilize around a 0-meter error. On the figure on the right, we can see that the satellite does experience some high control forces, but this is due to having a low tolerance on position and velocity difference in the LQR controller, as well as having a high mass of 100 kilograms in the simulation. Since the satellite can clearly follow the circular trajectory with low error, debris will now be added to the simulation. When it comes to the debris, it's randomly generated, like I had mentioned earlier, within a certain radius that is half of the satellite's orbital altitude, and that's calculated around the reference trajectory. Instead of a more traditional academic avoidance law, I had developed the algorithm myself, and it works in the following ways, like I had mentioned earlier. Sensing the debris, gathering data, extrapolating to get a predicted trajectory for the debris, determine if the satellite will impact with the debris' projected path, and then determining a new trajectory to track. And then once it's past the debris and it's within a tolerable range, return to the original trajectory. Moving on to the results of a singular piece of debris. With the figure on the left, it's the whole 3D orbit, including the debris. The scale is about 10,000, so that's why the debris looks like it's straight up and down, but really it's moving more at an angle. And then on the right, we have a zoomed in figure to show that it does in fact avoid the debris. But as you can see from the scale, this is hard to tell if the miss is in an acceptable range, which brings us to our next measure. To properly check if the satellite avoids the debris, the distance between the satellite and the debris itself is calculated, and then a norm of that is taken. In the figure on the left, we can see that we have that distance norm over time. And while it does increase initially, it's going to go close to 0. And since that's hard to tell with the scale, we have the zoomed in figure on the right, and we see that it does miss by about 300-ish meters in that small amount of time. So for one debris in the simulation, the satellite can successfully avoid it. As we can see on the left, just from the X, Y, and Z trajectory error, it does stabilize around 0. And then at the time that we previously noticed here, which is 4,110, it starts to oscillate as it avoids that debris. And then on the right, we have the orbital radius to show that it does have a 0 meter difference with the reference circular trajectory. As you can see, again, we have force commands that are kind of high. I had changed the gain slightly for these simulations. That way, it was a little more smooth and we could see the higher forces that caused the oscillating once the debris is within range. I move on to tracking a circular trajectory with multiple pieces of debris. As we can see, we have about 5 debris particles within this simulation with randomly generated around these reference circular trajectory. We use the same measure to determine the distance norm over time and make sure that's within acceptable range. And on the right-hand side, we can see that all of them hover above about 300 meters. Same here with the trajectory error over time. We see that it oscillates whenever it gets close to the debris, but then eventually will go back to stabilizing around the circular reference trajectory, as we see that with the orbital radius error over time as well. And here we can see that the forces oscillate as well compared to the singular debris simulation. And then I have a quick video just to show how the debris is randomly generated and then simulated to intersect that circular trajectory over time. And it's hard to see the actual avoidance on this scale. Picture.
Did we lose you? So I think, are you?
Hello?
Yeah, now we can hear you. I had some issues earlier.
Oh, okay. All right, I'll just restart the slide. So I have decent performance given the relatively simple avoidance algorithm.
I think we were okay here.
Oh, okay.
Okay, good. So yeah, your time is kind of up. So maybe if you can just conclude.
That was my last slide. So
okay.
All right. Any questions?
Yeah. Great. Questions, guys.
Yeah. So one question I have is in terms of the avoidance maneuver, is it like a deviation from the trajectory, or does it pause? Does it control the do you control the velocity, and how closest the debris come to the satellite? So these are.
So if you could still see my screen with this code, this is what I've actually done. So I'm just going to go around and give simple things. It just checks to make sure it's within a certain time. It gathers the data, and then from here, it'll just take the debris positions, and then from there, extrapolate those out to the orbital period. And then it finds if it intersects, and if it's within a certain tolerance range right here, then it goes into a while loop, and we'll just increase the orbital altitude of the trajectory. That way, It's just basically pushing the orbit out until it misses it within the certain tolerance. And then from there, it's just will return this new trajectory until it is out of the impact time it has been passed, or that the debris is out of distance. So right now it just really controls the reference trajectory that it follows in the LQR new trajectory compared to previously. But then once it's out of that error, then it goes back to the original reference trajectory.
Okay, thanks.
Yep.
Quick question. So the oscillation that we're seeing in the trajectory, I believe I saw some oscillation in the applied force. That implies that we're firing thrusters, say plus X plus Y direction. What's driving the natural frequency, the oscillation on that? And have you looked at possibly different tracking filters that allow you to do a more smooth thruster burn? So you'd have this, one kick to adjust one of your orbital elements, and then another kick to then recircularize your orbit.
I have not looked into other algorithms as far as doing that for the tracking, but I did mention in my further considerations, maybe doing multi-point potential field, but then also since I could select higher gains, so it tracks a little less, it might be smoother then, which will have less dynamic response, but that could also lead to actually having impact. So this was just, I found like a middle ground between the actual performance. But the missed distance for this was still around like 330 meters. So not terrible.
Okay. Also, final question. So the debris that you're modeling, is that co-orbital, or are you looking at higher closing velocity crossing type trajectories? I couldn't really tell on the graphic.
Oh, my bad. So currently the way that I generate it is I just have that one radius, which is half of my orbital radius. And then from there, I will just put this randomized location around the reference trajectory. And then I just calculate a linear velocity with it. So the debris doesn't experience gravity. It's just a very linear path going into it. A way to like expand that is if I actually made it like orbital simulation where it had circular trajectories as well.
Okay, got it. Thank you.
Yep.
I have one question. So did you use any sensor model for sensing? Because you mentioned that you were also sensing the debris. So I was just curious.
I did not use a sensor model. I just used sensing in a more general way. So I had about 100 kilometers sensing radius. So if the debris entered within 100 kilometers of the satellite, it would start to know its actual position of the debris and then track it for that extrapolation.
Okay.
But, yeah, so a sensor model could be incorporated in the future, as well as noise for extended Kalman filtering.
Great. Thank you. So let's, team 3, guys, can you share your screen?
Can you hear me?
Yep.
Can you guys see the screen?
Yes.
I can see it, Phil.
Yeah.
Okay. Let me go into presentation mode then. And there we go.
All right, so I'm Jonathan Lange,
I'm Phil Horn.
and our project was on a delivery drone. Next slide. So delivery drones have been gaining a lot of popularity in the last couple of years. You can see the Amazon Prime design and the Google Wing design pictured here. There's a lot of cool applications for drones that can deliver packages to different destinations with healthcare, food delivery, and postal. There's been I did some research and found some cool examples of using delivery drones recently, which are listed on the slide. Some interesting stuff too is the fact that Amazon, UPS, and Google have now all gotten FAA approval for their delivery operations and their designs. So that's a little background on why we chose, like, our motivation for our project. You can go to the next slide. So what we chose to try and do was we wanted to use what we had learned from modeling a quadcopter and doing different pendulum control to replicate a package being carried below a delivery drone. So our goals were to be able to define the equations of motion for this unique system, and then simulate the drone carrying the package and following a trajectory where the drone, it's the quadcopter is the part that's following the trajectory, and then once it reaches its destination, we want to be able to lower the package down to a drop position where the quad is trying to maintain a target drop location for the package itself. So that's kind of what we set out to do. Next slide.
So looking into the modeling of this system, there have been, I guess the baseline way to model this is using angular states. So a 3D pendulum can kind of be seen in this figure on the top right here, and it requires a constant radial distance, and it doesn't really allow for you to put other forces on that mass, or to be able to accelerate the point in which it's actually attached to. So it wasn't going to work with what we would like to do, or we would have to rewrite these equations. So the first method that we tried to implement was a tension-based method. And so essentially what we did is we looked at this free body diagram, and we set the acceleration in the direction of the string between the two masses should be equal to each other. And so by setting these equal to each other, we were able to find the tension and then apply that tension force to both of the masses in the direction of the string. And this worked pretty well, except for the way that we are modeling it. The solver because you're not actually allowing your constraints only in the direction of the string. So as soon as you get any sort of perpendicular, or I guess tangential to this circle motion, it's able to just to move around. So it doesn't really solve for the constraint of maintaining that radial distance. So the method we use in our final design is an elasticity method, and so it actually works similar to how this would actually work in real life with a string, and it doesn't have to just be at this radius. It can be within the radius. So essentially, we're just applying an elastic force whenever the mass goes beyond the length of the string. And so this is the most realistic model. You can kind of see it bounce if you were to decrease the elasticity here to be very small, or to be very large, but the mass is able to move anywhere within the circle of the length of the string there, and no angle states are required. So it simplified it drastically, and this is kind of what our whole simulation is based on. So for the purpose of this presentation, I'm not going to go into the things that are the same as the quadrotor system that we designed in class. I'm only going to focus on things that are different, just to maintain our 7 minutes we have here. So one of the features that we added were different control modes. So we have a fly mode, a drop mode, and a raise mode. And essentially in fly mode, it's the quadrotor is going to follow a trajectory. Drop mode, it's going to set the target and try to stabilize the package. And then raise mode is simply going to raise the package back up. We didn't do too much in raise mode just because it was kind of outside the scope of the project, but it's something kind of cool to work with. We added a wind generator, so that's going to generate a specified wind force, and then we added Gaussian noise on top of that. And then in our system dynamics, we added the pendulum position and the velocity states, and then we also added the string length, since we're going to want to move that around with I guess some sort of reel and moving it up and down. We didn't model that. We just said that we would give it a velocity that we're releasing the string, or bring it back up. Looking at the controller, this is pretty similar to what we did in homework 9 for our final quadrotor project, in that we have kind of this attitude controller, which is informed by the inverse block, and that's informed by LQR controller that's going to prioritize the position, velocity, and accelerations the trajectory. The one thing that we did add and change with regards to operates during the trajectory tracking mode is the LQR controller has been updated to account for the pendulum, and the inverse block now takes into the pendulum mass into account. So those are the big changes with in regard to the controller of the quadrotor during trajectory tracking. When we look at the drop controller, essentially drop mode enables the controller to pause the trajectory. So wherever you stop it, that's where it's going to set the target. So it'll give a north and east target straight down from the quadrotor. In reality, this could be anything, but that just made it easiest for us to simulate. So essentially what it does is it drops it, and it has proportional gain controllers on both the errors of the pendulum mass to where the target is. And then we put negative gain on here so that the rotes of the quadrotor actually moves over top of the pendulum mass in order to dampen it.
Hey guys, last 2 minutes.
So,
all right, so this is showing the results of our simulation. So in this mode, what you're seeing is the quad is maintaining its position and altitude with a wind noise. So you can see the package and the quad being blown in the wind, and the quad's maintaining control of everything by keeping its position. And then if you go to the next slide. So this one is our trajectory tracking. So with a wind noise, the quad is traveling around a figure-8 path and following that trajectory. So you can see the results of the actual versus the reference trajectory on the right. So it was doing pretty well at tracking that. And then this is the last one, which is the drop package control. So the quad is following a trajectory here, and then around halfway through, in a couple seconds, we initiate a drop sequence, and then it saves those target drop location values, and the quad is trying to get that package to hit that drop location perfectly. And you can see on the chart to the right that as it gets closer to the end of the chart, the pendulum position is almost perfect with the target location. So that's all we had. Any questions?
Thank you. So yeah, judges.
Great project. I just wanted to say that. Yeah, I have no questions.
I felt the
Show home, bro.
technique that you used was extremely good. I need to get my head wrapped around the math a little bit to validate, but I do feel you did a great job simplifying the dynamic problem.
thank you.
Okay. Anybody else? Other judges? Great. Thanks, guys. Good work. Nice simulation.
Thank you.
Thank you.
So team 4, Cameron and Jeff.
Yeah, getting it pulled up. All right, can you see my screen?
Yes, we can see it. Your time starts now.
All right. All right, so my name's Jeff Pickett, and working with Cam Farley, and we did the automatic Bullseye Quadrotor edition. So we talked about it a couple weeks ago in our mid-project review, but our motivation was Mark Rober's automatic Bullseye machine, which doesn't seem to be playing. This is a GIF. I'm not seeing it move. But anyway, you can see it here. Essentially, the dartboard will track the trajectory of the dart to ensure that you get a bullseye. And so our goal was to do something very similar, but to integrate it with our quadrotor simulation and control system that we designed to work. So the first thing we did was to adjust our quadrotor actual physical model. We assumed that our dartboard was hung rigidly under our quadrotor. We made it 60 centimeters in diameter. We didn't dive too deeply into modeling the physical properties of the full system, but we did want to make some representative changes in the mass properties. So we doubled the mass of the entire quadrotor system. We multiplied the moments of inertia by 4, just trying to be conservative. And then with that, we had to retune our attitude controller. And you can see some results from that going from the left to the right on those 2 plots in angle tracking. We made a simplifying assumption that the center of gravity of our vehicle and dartboard system was at the center of the dartboard, which, if you look at the way we drew in the upper right-hand corner, the way we drew our quadrotor in the MATLAB simulation, it doesn't look like that would be the case, but I see it's cut off a little bit. But in the lower right-hand corner, we tried to show, we did think a little bit about how it could be potentially made so that the center of gravity does exist at the dartboard center. So then we had to go ahead and simulate some dart trajectories. We created some code that would let us input launch angles and launch velocities for a dart, and the code would take care of the rest. We also had to create some logic that would allow the dart to interact with the dartboard. Essentially, does it hit or does it miss? If it does hit, output the data of where it hit the board. And also for the simulation, we want to now stick into the board and fly around with the drone. In terms of control methodology, we largely leveraged our LQR and differential flatness controller that we created in the homework. We did, however, have to tune for this application our Q and R parameters, which we did mostly through trial and error. In terms of sensing, we didn't dive deep into a sensor model or anything, just assumed a noiseless knowledge of the dart states after what we call a simulated sensor delay. We made the sensor delay 20 milliseconds for most of our runs, but essentially just after the 20 milliseconds into the dart throw, at that point, now the drone has full knowledge of the dart states. And then another thing to point out is we didn't allow the drone to move toward or away from the dart thrower after the dart has been thrown. We commanded it to keep its distance, essentially stay on that dartboard plane. And then in terms of creating a control system that allows it to actually catch the dart, we used trajectory control similar to what we did in the homework. And we experimented with 2 different main trajectory types. The first one being constant acceleration. So the drone would calculate after it becomes knowledgeable about the dart states, what constant acceleration does it need in all 3 directions and all 3 angles to meet the dart at the interception point perfectly with the right angles and location. And the second type was symmetric acceleration and deceleration. So similar, but this time it's going to have to accelerate faster over the first half so that it can decelerate over the second half and meet the dart at its interception point at a stop. Oops, I gotta go back. Sorry, Cam.
It's okay.
I should have done this not on Teams, but on PowerPoint.
So what I'm going to show here is, oh, it's still loading. Is a comparison of, so it's short little snippets of video comparison between the constant acceleration dart catch and a symmetric acceleration deceleration method for the dart catch, and you'll see the difference between those if it pulls up. So as you can see, it constantly accelerates and then follows through with no deceleration to catch the dart. And both of these were set up with the same initial parameters. I just set them up such that you could see they moved in a pretty good 3D space. So in that one, you can see the the drone has to, swing around in order to get the dartboard exactly to stop right where it needs to stop. You can go on to the next one. So I did some analysis statistical analysis on what we were actually sensitive to as far as the 3 initial starting parameters and their effect on the distance, how far away from the bullseye we actually landed. So I've performed a 3-factor, 3-level, full factorial ANOVA analysis on the constant acceleration control method, changing initial velocity, launch angle, and horizontal launch angle at those specified low, medium, and high values. And using Excel ANOVA analysis, determined that the primary, 2 primary effects, the initial velocity and launch angle, as well as their interaction, actually at a significance level of 0.05 or 0.95 were what we were most sensitive to. So for any given vertical launch angle, we tended to not change that much in how far away from the dart bullseye we reached. So if you go on to the next one, I also wanted to I went to go and do the same thing with the symmetric control acceleration, but I started with the initial conditions where A and C varied, keeping B at medium, which B was the vertical launch angle, which I found did not have much effect. But I found that it actually did not hit on 6 out of the 9 throws, only hitting at 3 out of the 9. So determined that it was not as robust to catching the dart as the constant acceleration control method. And actually averaging those 3 throws, even when it did catch, it was twice the average distance from the bullseye as the constant control. And we theorized that this is really due to 2 things. The quick lateral acceleration that you need in order to accelerate and decelerate. Actually, the thrust of that causes the drone to rise, which makes the dart consistently miss low. And then just in general, the time taken
Guys, last 1 minute.
Okay. The time taken to accel and decel is actually longer than if you just constantly accelerate to that target. So it can miss more often. If you go on to the next one for potential future work, we'd like to look at different alternative trajectories and control methods, implementing noise and some realistic sensor data. Take a look at what would be industry standard for, maybe computer vision or something to tell the drone where the dart was. And then also include aerodynamic forces, more accurate representation of mass and moment of inertia, and then also allow the quadrotor to move forward and backward out of its initial plane, which would increase the radius around the drone where it could catch the dart, because it could move further away or closer to it depending on how the dart was initially thrown. We did not include that because that would significantly increase the number of paths it could take to the drone. If you look at the last one, this is just a fun video that I put together showing that even with some initial rotational velocity, yawing, the drone could spin and orient itself around in order to catch the dart. So it does a full 360 here. And that's it.
Thank you. Questions?
Can you explain what the symmetric acceleration consists of, and how is it different from constant acceleration?
So the symmetric acceleration, these plots, I know I didn't have much time to let you look at them, but these are an example of trajectory, and it's shown, and this is the acceleration, here's the velocity, and here's the position. So in acceleration, the orange is the constant acceleration. So it needed to go down, so it just one constant acceleration, and the symmetric is what you see here. It's constant on each half of the entire trajectory.
I see. And is that computed as an error in the distance between the dart and the?
Yes. Yep. So the based on the knowledge of the trajectory of the dart after the 20 millisecond delay, the drone is able to calculate the dart going to be and when is it going to hit the dartboard plane. And then based on that time and distance, we then back out the acceleration that's needed.
And your overall result, is it that symmetric acceleration works better than constant acceleration?
So Cam can talk to this a little better, but we found for the most part that the symmetric doesn't work well.
Doesn't work well. Okay.
For longer distances, simply because it needs to accelerate faster so that it can decelerate. Whereas the constant acceleration gets to start kind of, you can see the acceleration the magnitude isn't as high here. So it can kind of smoothly ride through the dart, whereas this one has to really get it going fast and then try to stop, which creates quite a bit of swing as well.
Yeah, essentially, if you go down a couple slides,
this one.
So yeah, that one. Really, so the constant acceleration was able to catch all 9 of the throws that I designated here in the comparison, versus the symmetric acceleration only being able to catch 3 out of the 9. And it really has to do with the fact that the constant accel, we allowed it to accelerate through the dart and have a follow through, so it could be going a lot faster over that time versus the constant accel, which has to come to a complete stop at its target. So that time taken to accel and decel is much higher than just a constant acceleration. So you really lose out on the radius at which it'll be able to catch something by doing the accel and decel. Although it does look cooler in my opinion.
Okay, thank you.
Okay, last one question. Time for one question. And we will send all the slides to judges so that later on, if you want to take some more time to, so we can send the slides as well later on.
Sure, that helps.
Okay.
I had one question. Yeah, just a quick question. So you're not doing anything to track the dart, right? So you're assuming perfect tracking. Is that so?
Yeah, we're not doing anything to actively track the dart. No, we're essentially assuming that the quadrotor is knowledgeable of the trajectory of the dart after the delay, and the trajectory is predictable, so it doesn't need to continue to monitor it necessarily. It already knows where the dart's going to be.
Yeah, we assume that the dart has some CG and its initial launch angles and velocities remain the same, and simple Newtonian, kinematics allow us to say where the dart's going to be with negligible air resistance.
Okay.
Great. Yeah. Thank you. Cool stuff. I think I would like to have such a dartboard in my home. So let's get to Anirudh, team 5.
All right. Hi, everyone.
And your time starts whenever you put the slide. Yeah.
All right. So, hi, everyone. I'm proposing a unique robotic manipulator, and we'll look at this application in the next slide. So, we know that physical testing of certain space systems that are required for rendezvous and docking and space servicing tasks, it's very difficult on ground and it's very expensive to do in space. So what we need is hardware in this loop simulation environment, and we need platforms that can mimic the motion in space in all 6 degrees of freedom while offering a dynamic range of motion. So we have serial and parallel manipulators in 2 broad categories, and both have their advantages. Like serial have a larger range of motion along all degrees of freedom, whereas parallel manipulators are precise. Also, they have a faster response to the control commands. So here's an attempt to form a serial parallel manipulator by integrating a robotic arm on top of a parallel manipulator such as a steward platform. And so this is basically a steward platform. So I'll just go over the dynamics here. So this is the relationship between the 3 frames. So the base frame, the moving platform frame, and the limb frames. So there are 6 limb frames, and that's how we do the kinematics and form the Jacobians so that we can translate between the joint space and the general coordinate space. This is between the base and the limbs. And this is an overview of the whole dynamics, and we define all the characteristic robot equation in the closed loop format, and we define all the constants. So to form the dynamics of the integrated platform, what I did was I broke down the Lagrangian into two parts because I already had the dynamics of the steered platform. It's an old manipulator. It's available in papers and researches and books. So the first part here, L1, defines the equations of motion for the just the steered platform, and L2 defines the equations of motion for the robotic arm. So I wanted to do this for a 3-DOF robotic arm, but because of time constraints and I think some difficulty levels, I could only go to the 1-DOF. So we can see that there are two robotic equations here, and what we do is we add 0 rows and columns to the first one, because the new degree of freedom, that is the angle at which arm is from the moving platform, that only concerns the robotic arm and not the steered platform. So we can just use the existing dynamics by adding some zeros, and then we can combine both the dynamics as given here. And our generalized coordinates increases by 1, that is theta along the u-axis, which is here. And so this is like a frame diagram, and so we form the position vector and we get the velocity from it, the translational velocity similar. So here we also form the direction cosine matrix to define the relationship between the frames, and then we also define the angular velocity similarly, and we use it to form our total velocity vector, which gives us the kinetic and potential energy, and we can form our Lagrangian. So here we need the moment of inertia, and we define it first in the local frame and then in the global frame. And this was the dynamics. So because of the high nonlinearity, I was not able to check for the controllability, but when I looked deep enough, there was a way to check the structural properties of the derived dynamics, which can make it in a way controllable and say that it's a stable system. So there are two main properties. So property 1 says that the kinetic energy is 0 when the system is at rest and positive otherwise. So that means the inertia matrix is symmetric and positive definite, which came out to be true. And the second one is the passivity property, which states that in absence of friction or any other non-conservative forces, the net energy is conserved. And this also came out to be true. Because I derived the dynamics symbolically on MATLAB, so the MATLAB functions do not allow to check for such things on symbolic variables, but you have to do it numerically. So I had to parse through all the variables, and because of the number of dimensions, I could not find a way to visualize these results. So this is a basic attitude and position control. This was another step basically to verify if I'm going right. So giving, like, let's say I want to say a commanded X position. So I give that, it gets the force from it. It uses the Jacobian that we saw before to convert it into the forces that are actually applied by the limbs or the legs of the steered platform. And it was working fine. So I went ahead and tried to make the trajectory controller. But one thing that I did not consider was that that I had to explicitly define the kinematics between the end of the robotic arm and the complete steered platform. Basically, that would give me the conversion through which I can define the trajectory from a global space into the general coordinate space.
Anirudh, you have a last 2 minutes.
Yes. So that was an issue, but what I did was I defined a trajectory directly in the general coordinate space to verify, and these are the kinds of results. So we can see I gave like a fixed angle to the robotic arm and a circular trajectory to the steered platform, and you can see the errors are very low, especially in the attitudes, 10 to the power -3, -4, and that's in radians. And even in the XYZ positions. Either it oscillates around 0 or it settles at 0. And in the Y, the oscillation is less. And I think that comes down to the high nonlinearity and the basic control that I've used, the PD control. Similarly, in the velocity and in the angular velocity, the errors are quite less. And what I'll do is I'll go ahead and show you the simulation. So when I run it, so in a second it will start following the trajectory, and you can see that the draw file is not that good, I guess, because it's stuttering, or is it my laptop? But it is going around in circles, and we can see that the robotic arm is at a fixed angle that is pi/4 when compared to the moving platform on the top. So this was working fine. And so I think the primary conclusions that I drew were that now I actually know how to use Simulink to do all of this. And so we learned about differential flatness for UAVs, and I realized that why is it a really good method to set up this model, because I tried to use feedback linearization and LQR, but it was very taking a lot of time. So I even tried to solve the Risati equation, but that wasn't any good for now. So yeah, differential flatness also allows to basically do that conversion from the trajectory defined in less degrees of freedom to the whole system. And other next steps that are required are that I need to explicitly define the kinematics and the Jacobians so that I can have that system for future trajectories, and I can go ahead and expand this to a robotic arm with more degrees of freedom, and I can add some noise and disturbance to develop a more robust control law. Thank you.
Well, good job, Anirudh. It's very courageous to play a real-time simulation sometimes.
Yeah.
So awesome. Yeah, couple of questions. Time for a couple of questions while Team 6 gets ready.
I have one question. Like, did you incidentally constrain your arm to not move, or is the arm free to move?
The arm is free to move. Actually, the desired trajectory that I gave it keeps it at the same angle. So
okay,
and the
so
velocity
you have
is 0.
2 degrees of freedom here, right?
So I have actually 7 degrees of freedom. So basically, if you see, this is the steer platform. So it can translate in all 3 axes, and it can rotate about all 3 axes. And the 7th degree of freedom was the robotic arm.
Okay.
Which was the angle between the robotic arm and the moving platform. So it's like an inverted pendulum on the steer platform.
Okay, thanks.
So what are the main target applications of such a system?
So basically, when we are looking so for example, in space, we have some old satellites which are old, but they are important to us because they are doing some important work up there. So when we send the newer versions, and sometimes the old satellites are not equipped to follow the, let's say, the docking procedures. So we need the new systems to be able to properly track those and perform the docking procedure efficiently. Now, to do that, we need to study contact dynamics, because in space, if you touch something wrong, even with a small force, it can go offline. So when you do that, the analysis for the analysis of contact dynamics, you basically need a simulation platform, but it needs to include the hardware within the simulation environment so that you can understand how those contact dynamics actually work. Because in a computer simulation, there are a lot of approximations which can lead to basically not wrong analysis, but incomplete analysis. And does that answer your question?
Sure. Yeah. Thanks.
Okay, great. Thanks, Anirudh.
Right.
So let's go to team 6.
All right, can you hear me?
Yep.
Alrighty, so I'm Zach Deutscher, and Josh Pevitz and I, we worked on a UAV variable payload adaptive control system. Next slide. So basically, what we did is we took the dynamics, or the Quadrotor simulator that we developed in class, and we modified it to where the control system gains would change as payload varies for a drone. And the overall applications for this would be any UAV where the payload varies throughout operation. So where a payload would be decreasing would be like drone delivery, or even like a firefighting drone that's dispensing firefighting fluid, or where payload is increasing, like possibly like trash pickup drone or something like that. But we'll get into the application of the controllers in a little bit. Next slide.
All right, I'm going to go ahead and walk through the dynamics, which we didn't spend too much time focusing on because we wanted to focus on the control. So we added a payload mass to our quadcopter at a fixed distance r, so it was rigidly connected. So you can see this green mass. We were able to change the mass of this payload dynamically throughout the simulation. To go ahead and simulate the effect this would have on the quadcopter, the CG was not moved. However, a torque was applied at this distance arm, moment arm, and the resultant torques are shown here. Because it's rigidly fixed at the center of the quadrotor, there was no change about the Z-body axis. And also for our maximum payload weight, we assumed about 3 kilograms because the quadcopter was given a typical thrust to weight ratio of 2 to 1. Let me take a quick scan through here and make sure I hit everything. We did not vary R because it would have the same effects with the simplified dynamics as adjusting the payload weight. And the payload weight, we did say it was assumed to be known by our trajectory controller, but not our attitude controller. For our attitude controller, we used an MRAC, which stands for Model Reference Adaptive Control. We used a slight variation on this. Typically, an MRAC would create a model plant, which in our case would be the quadcopter without a payload, and compare that to the true plant, which is the quadcopter with the payload, and take the difference in attitude to create an error state or an error value. However, we adjusted this by removing one plant, the model reference plant, and passed through the commanded attitude straight through to create an error. This significantly reduced compute time. With that error, you go ahead and multiply it by the commanded attitude or the model attitude, and then go ahead and multiply it by a gain, integrate it to get a beta value, which is then multiplied by our resultant torques. So this PID controller is the same one that we had previously used to control the quadcopter. So you can see how this beta value can increase or decrease the torques, the control effort going into the quadcopter to reduce the difference between the actual attitude towards the commanded attitude. This gain is a learning parameter, essentially. Higher gamma leads to quick responses, but can potentially lead to overshoot. And higher gammas we also saw cause longer compute time. So with a sensitivity study, we found that in this case, with our computing power, a gamma of about 300 was reasonable. Moving on to the trajectory controller, I should mention that this system does not require that the attitude controller does not know the payload mass. For the trajectory controller, we did use a control technique where the trajectory controller knew the payload mass. Is very simple. We saw that it required more control effort with additional mass to keep the correct trajectory, and so we increased the gain matrix with another gain, kg, which was proportional to the payload mass. So as payload mass went up, kg went up linearly. Again, similar to gamma, we saw that high kg values led to longer compute time, and so we did a sensitivity study. And an improvement of this controller would just be to change it such that it did not know the payload mass. I'll go ahead and let Zach talk through the results.
Alrighty, so on this slide, we're showing the baseline results. So both of these plots are the system without any adaptive controls implemented. The one on the left is a 0 kilogram system, and it performs very well, similarly to the way the original quadcopter simulation error set up. So you have your trajectory error, position, your velocity error, and your attitude error. And then as soon as we add mass to our system, those errors increase significantly. So the goal of this whole project is to get those errors down. Next slide. So these are the results with the adaptive controllers implemented. The one on the left is 0 kilograms, and it's virtually identical to the unaltered simulation error, which is good because that means our adaptive controllers aren't working when they don't need to. And then on the right are the error results for a 3 kilogram mass, payload mass, and the resulting errors are much lower than they were before, within a reasonable level of operating error. And then in these two videos are shown simulations of the Quadrotor. The one on the left is the one without controllers, and the one on the right are with the adaptive controllers at a 3 kilogram mass. And they're following a circular trajectory. As you can see, the one on the left has a lot more trouble following that circular trajectory, while the one on the right is able to achieve the desired trajectory. Next slide. So we also did a quick transient analysis to show that the controllers will adapt in operation with while the so on the left is a 3 kilogram to 0 kilogram transient at t equals 30 seconds. As you can see, but first the error is on the same levels as it was prior.
Guys, last 1 minute.
All right, are on the same levels as the as seen on the previous slide, and then when it goes to 0, there's no overshoot, so the adaptive controllers are adjusting properly. And then on the right are when the mass increases from 0 to 3 kilograms, and once again, no real overshoot, and the error is consistent with results seen before. Next slide. We'll start trajectory so Josh can talk about the findings.
Sure. So we found that adaptive attitude and trajectory controller did improve control of the quadcopter significantly as payload changed. We did see that the methodology still had some faults. We couldn't get the error all the way down to 0 as it was without a payload, and that it required significant compute power. So real-time computation is unlikely for implementation. And lastly, the LQR gain scheduling and the MRAC need to be used in conjunction. One without the other did not produce good results. And I think that's it. Are there any questions?
Great, thank you guys. Open for a couple of questions.
I have a question. What kind of parameters do you look at in order to design your adaptive controller?
The primary parameter is gamma, and through these attitudes are just phi, theta, and our yaw rate. Does that answer your question?
Yeah, it does. Yeah, thanks.
In the attitude control, at least, and then in the trajectory control, it's our position and velocity trajectories.
Okay.
Any more questions from these guys?
Is there an initialization penalty once you start to get this adaptive control mechanism up and running? And the reason why I'm heading there is that given your computational load for different masses, moving from one optimization strategy to another, you could potentially have multiple control rules. and then you can choose between them as your system changes physical state. But then the question is whether the system startup would allow you to do so smoothly.
It's a little bit about beyond the depth in which we went. Are you saying that we could change this gain for each air state? Because we could do that, which we didn't.
Okay, yeah, just potentially as something to consider. And in order to do that, you'd have to understand the system stability as you start your controller. So basically, your ability to respond to your initial conditions, however the air vehicle finds itself when I change control laws.
Okay. I think I follow. Thank you.
Great. Thank you. Thank you, Michael. Let's move on to Team 7, Austin and Nick.
All right.
Okay, guys, your time starts now.
Okay. Well, this is Nick DeGroote and Austin Wessels, and our project was about controlling a chase vehicle to track a target vehicle in a camera frame. So to give a brief description of the project, first off, we have two aircraft. I'm going to go in the presentation mode, sorry. We have two aircraft. One has a rigidly mounted camera, and it's tasked with moving the target aircraft into the center of the camera frame. This was inspired by some highly agile quadcopters. So you have like race quads or acro quads, which have that camera rigidly mounted. They don't have a gimbaling system. So the target can move along any trajectory, and I want to make it clear that the trajectory of the target aircraft is unknown to the chase aircraft. And our goal is to keep the tracking distance constant between that chase vehicle and the target vehicle, as well as keeping that target in the center of the camera frame. So as far as the information we know, we have the 12 states for the quadrotor that we're controlling. We have the target location in the camera frame, and we assume that we know the relative azimuth angle from the center of the frame to the target, and as well as the relative elevation angle. And then we also know the linear distance to the chase aircraft. Awesome.
Okay, so let's kind of describe in pictures what you just heard in words there. So you can see this diagram here that we have of our scenario with the quadrotor being the chase vehicle and the fixed wing aircraft being the target. You can see we have the heading as the state of the quadrotor, and then our relative azimuth angle is beta. So that's essentially the difference between the heading angle psi of the vehicle and kind of the relative position of the target vehicle. And again, we don't know where that target vehicle is heading. We just know its relative angle from the chase vehicle. And so then if we look at the side view here, you can see that in the axes, this is in looking to the right is along the beta direction. And then we also have the down direction. So we have the state of the quadrotor being theta, the pitch angle. And then we also have alpha, which is the relative elevation angle between the chase vehicle and the target vehicle. So from alpha, if we know alpha and the distance between the two vehicles, d, we can calculate h, which is important for controlling the relative angle. So we'll actually use alpha, or we'll use h to control alpha because they are very closely related, and it makes more sense to control h because we can control the thrust and the vertical axis of the body frame of the chase vehicle. A more interesting kind of scenario, instead of just chasing the target vehicle, will be orbiting the target vehicle. So you can see there's psi and beta defined there, and then the chase vehicle will actually orbit around the target vehicle in that circle of a given distance that we set. The equations of motion, these are just the ones that we had before for the quadrotor. We're just using the same dynamics that we've used so far this semester. So here's our essentially the feedback control that we used to maintain our distance and then try to minimize alpha and beta. So you can see here our thrust is controlled by that H parameter that we defined. Phi is controlled. We're trying to maintain zero horizontal velocity. Theta is controlled by the error, the distance error, so how far away we are from the vehicle, and then our heading is defined by beta, the relative azimuth.
And this is the Simulink model that we used. So it's a similar structure to what was used earlier in class for the differentially flat quadrotor, except now we're not assuming that the system is differentially flat. So we're creating a trajectory that directly models the target trajectory. So we got a couple of simulation videos here. So here's the first one. So first off, we're just trying to track a straight line. So over here on the right, we're modeling the actual view out of the camera. So this is simulating the fixed view out of the actual camera on the quadrotor. We did weight things a little bit, just a little bit, so that we gave a little bit more weight for the tracking distance than the elevation angle, because we decided that as long as you're keeping it in the camera frame, then you're accomplishing your goals. So that's the simplest one that we tried. We'll go ahead and move on to the next one. Maybe. So this is the second video. So for this one, we've still got a straight line trajectory that we're following, but this time we are orbiting the target vehicle instead. So we can see that we're our view is changing as we're flying around in a circle. And let this video play out. And the next one, oh, I missed one. Okay, so this one we are trying to track a circular trajectory. The chase vehicle is flying in a circle, and we're trying to maintain that 5 meters of distance at all time. So again, our chase vehicle is just going to keep following it. It doesn't know where that target is going to go, so it's just reacting to it at all times, trying to figure out how to keep its distance. Then for the final situation, we had struggled a little bit more with this one, just because there's more direction changes for the target vehicle, but for the most part, it still does an all right job. There's a couple of jumps in the elevation angle, but it's still able to keep it in the camera frame for the entirety of the simulation. So I suppose if I'm not out of time, I'll just briefly recap these plots.
So just wrap it up. Just a few more seconds. Okay.
So over here on the right, these are all the same for each of these simulations. We have the total tracking distance, the azimuth angle, which is the yaw direction that we're controlling. So the horizontal error in angle, and then we have the elevation angle error over here. And that's all. Any questions?
Awesome. Thank you, guys. Just one question, like, did you assume that Quadrotor is flying faster than the fixed wing UAV? Is that a fair assumption, or it can be?
Yeah,
I had the same question.
Yeah, we are assuming that. I mean, quite honestly, if your fixed wing is flying much faster than your quadcopter, you're not going to be able to do a ton about it. I mean, we could make some additional assumptions, like if we know that we can't keep up with it, we can keep the camera pointed at it for as long as possible. But yeah, it's not really going to work.
So your circular trajectory and figure 8 trajectory were cases, but when the Quadrotor was flying around a circular trajectory around the fixed wing UAV was, I think, can be challenge, but that's all right. I think the circular and figure eight were, even the quadrotor, because it was not flying too much, it was just changing its direction, right? So
yeah,
okay.
We can, yeah.
Any more questions from judges?
Not a question, but I think future work that will be fun for this is add state estimation to it, primarily because you shouldn't be keeping a certain distance when you try to estimate the state. So I just think it'll be a fun exercise for you guys for future work.
All right, yeah, I agree.
An interesting similar problem is to minimize the distance and turn your chase vehicle into a missile, I guess.
Great. Thank you, guys. If no more questions, good job. Let's move to project team 8. James?
Yep. Can you guys hear me?
Yes, I can hear you.
Okay. Let me pull up my screen here.
Okay, your time starts now.
Okay. So, let me switch here. All right, so good morning. I'm realizing that I'm going to have to blaze through these slides because I've got 30 of them and not a lot of time, so I apologize if I seem like I'm going pretty fast. My project is multivariable control of turbojet engine and aircraft pressurization systems. So in an aircraft, compressed air to pressurize the cabin is provided by the jet engine, which in turn also produces thrust. These two systems are coupled such that the more air that the aircraft cabin draws is less air for the jet engine to use, and the faster the jet engine spins, the more compressed air that it provides. So power setting and aircraft cabin pressurization setting are coupled in that manner. The basics of a multivariable control system are, so the diagram shown here, where U1 has an effect on both Y1 and Y2, as shown through GP11 and GP21. Input U2 has an effect also on Y1 and Y2 through GP12 and GP22. Adding a controller to this, a feedback loop, yields the following, where the only difference between the previous slide and this one is that now there's GC1, GC2, and a feedback. You can see that, for example, if we're looking at input U1, there's the primary feedback loop, which is just the classic feedback control loop. However, additionally, there's this secondary control loop where input U1 goes through GC1 through GP21, where it's fed to the output Y2. That's fed back through the feedback to GC2 through GP12, and then eventually back to GC1. So when designing these controllers, careful considerations have to be taken for not only the primary loop, but also the secondary loop as well. A lucky situation is where U1 doesn't have a very large effect on the output Y2, and input U2 doesn't have a very large effect on the output Y1. In those situations, GP12 and GP21 can be approximated to be 0, and then you're left with the classic two independent systems with a simple feedback loop, as shown by the red and blue loops here. So when approximating the jet engine as a dynamic system, I went ahead and thought of this shaft connecting the compressor and the turbine as being rigid, so there's no potential energy stored in the twisting of that shaft. So I can simplify this as some mass with inertia J, there being an applied torque to it, and some bearing friction as denoted by the dash pot here. Going through Lagrange's equation, the equations of motion turn out to be J theta double dot plus B theta dot is equal to torque. So pretty darn simple. So what is torque? Torque is the difference in the torque provided by the turbine minus the torque consumed by the compressor, so the net torque. Rushing through these equations, you have the equation for the torque provided or consumed by the compressor as a function of some of the thermodynamic properties. The torque provided by the turbine also as a function of some of the thermodynamic properties. Therefore, the torque, net torque can be, the difference between those two. Summing, adding this to the equation on the previous slide, you get this larger equation here. An additional, I need to skip through these because I'm taking too long. So the input to the system, it comes from this fuel flow. This is where the fuel is added to the combustion chamber. This is the combustion chamber temperature rise equation here. TT4 is then injected into this equation, which results in an increase in torque. Again, I apologize for going quick. I know that I'm getting short on time. So when you solve for TT4 and the combustor temperature rise equation, combine these all into one equation, the previous equation where we solved for torque, you get this equation here where the red items are functions of the engine speed itself. And some examples of that are shown here with compressor efficiency, which is A to C, and then turbine pressure ratio, which is TPR, as some examples. This nonlinearity makes it extremely difficult to solve analytically. So I chose to go a more simulation-based path. So modeling in Simulink, as an example, here's a compressor. This is the torque equation from the compressor that was shown earlier. You can represent this. Here are the variables that were functions of the rotor speed N. So you can discretize it and simulate it in Simulink as opposed to trying to solve this analytically. Similarly, here's the compressor or combustion chamber temperature rise equation, the turbine torque equation as well, modeled in Simulink, and then the dynamics, which were the if you simplify the equation that we found from Lagrange, you can get theta double dot as a function of the difference in torques minus the bearing term over the inertia of the rotor. And this is shown here in the Simulink diagram below. Moving on to cabin pressurization. So there's a pressure range that the aircraft cabin has to maintain. If you assume that the density inside the cabin is relatively constant, then you can assume that the mass flow in has to equal the mass flow out. And you assume that there's a constant mass flow out of 5 kilograms per second. Starting from the ideal gas law and making some assumptions as shown here, which can be reviewed later after the presentation, you can get to the change in pressure over change in time is equal to the mass flow in from the jet engine minus the 5 kilograms per second that's leaving the control volume, which is the aircraft fuselage, times the thermodynamic quantities here, RT and V from the ideal gas law. Modeling also this in Simulink can be shown here. So back to the multivariable control. So as example for this problem, initially what I thought was there was going to be a throttle setting that would have an effect on engine speed and also cabin pressurization, and there would also be a cabin pressurization setting that would have an effect on engine speed and cabin pressure cabin pressure as well. Yep, just summarizing what here. So these two inner terms are the effect of cabin pressure setting on engine speed and the effect of engine throttle setting on cabin pressurization. So those cross effects that happen in multivariable control systems. So as to gauge the effect of cabin pressure setting on engine speed, I went ahead and set the fuel flow at 3 different settings. So I turned off the engine control system itself, and then set the cabin altitude to the lower limit, which was 6,000 feet, and the upper limit.
Last one.
Okay, all right. Long story short, their GP12 is negligible. You can see the percent change is essentially 0. So GP12 can be eliminated. There is a pressure regulator that is upstream of the inlet flow to the aircraft cabin. So as long as the air supply pressure is greater than the cabin pressurization pressure, then GP12 is exactly 0, because you're going to get whatever mass flow that you require as long as this is greater than your cabin pressurization. So these are essentially 0. So our multivariable control two systems broke down to the simple control of two independent systems. So I utilize a PID controller for both. Here's a PID controller for the engine control speed. I can't talk about anti-warm-up right now or anti-wind-up right now. Here is a burst. So from idle speed to takeoff thrust, this is commanded fuel flow, and this is engine RPM. This is a Bodie, so it's typical for a landing scenario where we go from approach idle to ground idle and then max reverse thrust. So as the aircraft is landing, you can see that here's our elevated idle, here is ground idle, and then here is reverse thrust, corresponding fuel flow. Altitude control was also done with PID controller. Here is the mass flow rate of air and the cabin pressure setting going from the upper limit to the lower limit. Okay. So power setting and cabin pressurization setting are not as interconnected as initially thought. So our two system broke down into two independently controlled systems very well. PID controllers were used, but we could go for more efficient controllers. The turbine inlet temperature was not controlled. Fuel flow should be limited during engine transients, so to limit TT4. And the analytic analysis might be possible if lookup tables that was an example of the compressor efficiency or turbine pressure ratio could be approximated with curves. So I think that an analytic analysis might be possible, but I'd have to look into it. I didn't have time with this project. Whew. Okay, questions?
Great, thanks. Very time for quick questions.
Yeah, I apologize.
So James, how much of this work was current project or like when you doing this somewhere else also? Like seems like lots of slides to be doing for this project.
No, this is it. This was originated with this class, and it went a lot of different places I didn't think it was going to go. I think that's why there's a lot of slides as well, because I initially thought this was going to be pretty straightforward.
Okay. Okay, open for one quick question from judges. You guys.
Sure. Again, I apologize for talking very quickly. If you review the slides and have any questions, please feel free to email me afterwards. I'd be more than happy to discuss or get your feedback.
Yeah, so it's interesting to notice that cabin pressure can tax on the engine performance. So that.
Yeah, because if you're taking away different quantities of mass flow that you put in work from the compressor into that airflow, then that changes your air to fuel ratio, for example, changes the turbine inlet temperature. It changes a lot of parameters throughout the engine. Although it showed that the effects were negligible, it does theoretically have an impact.
Great. Yeah, thanks, James. Okay, let's go to the 9th team. We're getting at the end. So.
Hello, can everyone see?
Okay, your time starts now.
All right, so my name is Alex Minton, and my partner's name is Karl Mueller, and we're doing autonomous quadcopter delivery system, as you can see over here with the package and the quadrotor. Good. So our problem statement, as we know, packages are predominantly delivered by humans, and this is both costly and tiresome. And the problem with ground-based delivery robots are that they're subject to surface conditions. We also know that autonomous vehicles are maturing rapidly and have potential for use as carrier drones to mitigate the limited range of drones. So our control objective was to fly a quadcopter from a flatbed truck to the porch of a house to allow delivery of package. And then after it's made its delivery, it'll go back to the flatbed of the carrier. The big objective overall is the pathing, optical avoidance and dynamic pathing to the truck. That's what we're really concerned about here. So we propose a system that would have an aircraft carrier, such as this big vehicle in the background, and it has onboard quadcopter drones. The truck would drive through residential roads, and the drones would fly to their destinations. These are the equations of motion. A lot of other teams have hit on these, but this is basically from class. As you can see, we used the body frame of motion and then PQR also. But yeah, we won't get into that very much.
Note though, in the control path states, we have PN and PE, but PD will be set to 0. That is just for the sake of simplification of pathing. We're going to assume that the vertical direction is planar.
So this is a simplified version of our control system. As you see in the top right blue box, we have a PID controller for attitude control. In that, I'm not sure if that's green or yellow box, has LQR controller, which basically is our differential flatness controller, as we had done in class, but it's a little bit different as far as how we track the X position. And then we have the gradient trajectory, which Karl will touch on later, as well as the generation of the waypoint and the gradients, as you see on the left box. This is our LQR controller, just a basis of how it was derived. We won't get into that, but that's, if you want more information, that's where it's at.
Yeah, long story short too, it's feedback linearized and there's a small angle assumption.
And we use Bryson's rule for this LQR controller. If you want to pick up where we left off, we used these Q and R values along the diagonals. But yeah, we won't get into that either.
Okay, so now we're getting into the control methods. So this is just a brief overview, and you can read this here, and we're going to really step through it on the next slides. But the main goal here is to demonstrate that it's waypoint based and based on descending gradient. So to generate a path, we generate potential fields. An example of which is on the right here. This is actually the last example you'll see in the animations. So the potential field acts as a path in the goal states. The blue shows low potential. Are low potential areas defined by a negative Gaussian, and the quadcopter is meant to track towards those low potential areas. The obstacles are areas of high potential, as you can see with this amorphous red and yellow blob. The quadcopter is meant to avoid those areas by means of gradient descent, and it should move around the obstacles and into the finish line. An interesting property of these potential fields is that the way they're defined in this program, they're summative. So I can take the goal state matrix, essentially, which is just all of this from the low potential contribution, and then add obstacles on top of it so that they add potential in certain areas that I want to avoid. And that makes it easy to redefine these. So this is a different approach towards gradient descent. I just call it modified gradient descent. But essentially, we are setting waypoints for the LQR state controller to point our quadcopter towards. So if you look at the equation on the right, we have our actual position north and position east. And then we add the negative gradient in the north, in the east direction of that potential field. That's all multiplied, or the gradient negative is multiplied by a scalar alpha. And that alpha essentially just multiplies the distance. So as we can see on the chart here, if our copter is this x and our gradient vector at that given position is this red arrow, we just add that gradient vector times that scalar, which really gives us our sensitivity to that gradient or some sort of rough rate that we want to move at. We set a new position waypoint. And this happens, one, on the approach path. So as the copter moves to the house to deliver, it acts like this. And then on the return path, instead of using the gradient, we use the heading which is just the difference vector in between the position of the quadcopter and the truck. The states of both are known, and we just essentially add some multiple of that new heading vector to the current states to set a new waypoint. And these are very iterative. They happen in very small increments at each position step. So in the simulations, you'll see our copter here, and this is just a sort of a equipotential plot. So you can see the obstacle clusters are going to be these areas of high potential, and delivery destination is going to be our low potential. So we're going to track towards there. And here you can see the quadcopter navigates around the obstacle and towards the area of low potential. And then you could see where it changes direction sharply. That's actually once it hit the delivery area. And this progressing red line represents the state of the truck. So the truck is at the front of that line. And right as it drops off the package at that center, the copter redirects towards the line, towards the truck, I should say. Here's another example that's more of a challenge case. So note the obstacles are in directly the way of this sort of blue ideal path. And the quadcopter is forced to navigate around these and then come back to the truck. These are just some attitude outputs. So we'll note that the attitudes it's very sharp and spiky in a lot of spots. That is mainly due to the quantized nature of the potential field and the gradient. It's only 350 steps in either direction, so we're going to see some blocking. It's fairly low magnitude across, so we can see that it's relatively smooth input, though it changes sharply due to that gradient change. And this sharp peak in each of these represents the position where the quadcopter actually turns around and reroutes back to the truck. And you could see that happen pretty quickly in the animations. So as far as positional states go, we can see that it tracks relatively well. In some areas, the reference position actually tracks up and down with regards to the actual position, but the physical constraints of the system actually help to smooth that.
Guys, last 1 minute.
Sure. By increasing the resolution of the gradient and the potential field itself, these artifacts in tracking can go away. And then here are just some error plots, relatively low error in terms of power angles. So relatively low error overall, except in the case of, again, here at about 110 seconds, we see a spike as it jumps back to the truck. We went through a few other approaches in approaching this issue. Many of them involved actually applying a force to either roll the quadcopter away from an obstacle, and this force was proportional both to the distance. So as the copter would get closer to an obstacle, it'd be pushed harder away, or if its heading was pointed right towards an obstacle, it'd be pushed away harder. So I'll go over localized annealing quickly. So if you see on the bottom right, potential fields have an issue where if the copter gets stuck in an area of local low potential, it doesn't move because the gradient there is essentially zero. We thought of a method called localized annealing that could be a good next step where if it gets stuck in a low, it increases the potential of that local area until it exceeds that of the area around it, and thus a new gradient is formed. And the copter can sort of roll down the hill away from that high area and back onto the field so it can find the true low. Alex?
Yeah, and another idea that we had was to give the quadcopter somewhat of a memory for those local minimums whenever, like let's say it's at the end of a maze and it needs to turn back, it would go back to a point where it had another viable decision to turn in another direction, so that could make that alternative decision at that point in memory. And also, if you go back to the previous slide, we were thinking about using a proximity sensor to approximate about 5 meters around the quadcopter. But we had to scrap that and that EKF method that we were trying just to put it in a more simple way with the quad states. So we were trying to go that way, but we realized that we didn't really have the expertise to do so. So we kind of changed our course and went with this model instead, since it's very reliable.
It gets pretty computationally intensive as well to recalculate the gradient every time that it sees an object, but I'm sure there are ways around that. Questions?
So I wasn't sure. Are you guys using the state estimation in the end or not?
So we don't use state estimation. The coordinates of the quadcopter, the truck, and the goal states and the obstacles are all known to the system.
Okay. Okay. And what if there's an obstacle in the path of the return that is from the house to the truck?
Okay. So if we go back to this animation, this one shows it somewhat well. So essentially, the way this works is the tiny vectors that are being applied to the quadcopter position that set the new waypoints are influenced by the position of the goal, and then also the potential field.
So basically, the artificial potential field is also present on the direction of the return, even if it is a quick maneuver.
Yes. So the copter itself points back towards the truck, and in the case of the copter returning to the truck, I actually removed the initial goal potential contribution. So the only potential field left is are the obstacles. So it navigates away.
Okay. Okay. And isn't the new goal the truck itself? So wouldn't that contribute to the potential?
It does, but in order to save computationally, the truck doesn't have potential, but the truck contributes to the waypoint generation. Okay.
Okay. You might want to, saturate the velocity while on the path of the return. It's probably, in simulation, it's probably possible. I don't know. In hardware, there might be a physical limitation on how fast it can return.
Yeah, thank you. There are some limitations in the PID, but it still lets you give off quite a bit of force in any lateral direction.
Right. All right, thank you.
So thanks. So before I think that the last presenter puts the slides, do you also play with when the quadrotor should get out of the truck? Like I saw places where seems like it could have stayed on the truck for a while, and then when the obstacle was gone, then you fly. So optimization from initialization perspective, where should it fly from? That can be an important aspect to look at too.
Okay, that's good feedback. Thank you.
Any other questions, Krishna?
Yeah, one thing is, do you assume that you have obstacle information before path generating the path? I think so. Correct?
Yeah.
Or just is it based on proximity, or you sense and use that to update your potential field? And other question is, how do you extend this to a moving obstacle situation?
So as it's set up right now, the whole potential field is known to the system at all times.
I see.
The path itself is dynamic, dependent on that field. But right now it knows everything, and that a good next step would be to only factor in obstacles fields once it can see them. In terms of moving obstacles, we may need a slightly different approach. I was trying to actually model the truck as sort of a movable goal using the potential field from the onset, but I ran into issues with recalculating those fields at every time step. It slows down the simulation really quickly.
Okay. Just great. One more question is, like, how does Simulink, how compatible it is to perform real-time, like, replanning?
Did you say replanning?
Replanning, yeah, based on changes in obstacles or correct? Presence of new obstacles, for example, it doesn't have to be like moving, but some obstacle just appears, correct, which you haven't taken into account. Or
Sure. Yeah, I'm not an expert at Simulink. I just started getting into it with this class, but I feel like this method at least would be pretty robust to that. I think if we recalculate the field and it's not directly underneath the quadcopter, I think it still would track very well.
Sure. Yeah. Thank you.
Yeah. And
Awesome. So let's get to the final presentation of this semester, I would say. So, okay, your time starts now.
Okay. So my presentation is my project is slightly different from the previous project. It's more like a verification for my crazy idea, and which is monocular RGB camera depth estimation. So this project is still in the early form, and I just finished the fundamental part. I will show, but you can see something from my result. I will show you later. So, okay. So this is the table of contents. So first part is the problem definitions. I guess you have already heard the problem before. So it's using only one RGB camera to estimate the depth information of the surroundings, which is, I think it's a very difficult problem in SLAM. And the second part is the progress I have made so far. And the third part is the results I got so far. And the fourth part is the conclusion. So it's very popular to use a LiDAR or a depth camera in the SLAM, in solving a SLAM problem. But I'm trying to use a single RGB camera to do this. This is because if we're using a RGB camera, we can save a lot of money. You know, this LiDAR is very expensive, and RGB camera is usually very cheap. And the problem definition for my project is a mobile robot is moving along a given trajectory with a single RGB camera on it. And I assume the robot can get its ground truth coordinate information, so there's no error in the sensing its location. And the robot need to estimate the depth information of the object based on the camera image. And this is a process I made for this problem. First part is build an environment for build a simulate environment for this problem. And the second part is algorithm for feature detection and triangulation. So I was using triangulation for detecting the depth information. And the third part is result, and the first part is improvement. So for this problem, I'm using ROS and Gazebo for the simulated environment, and they are totally free. So I think it's a good option. And this is a world I'm designing for the robot. Those spheres are randomly placed by me, and they are the object in the environment. The robot need to robot can move in this world and detect the depth information of its of what it have seen, and specifically in this orb. And here is the robot model. It's very simple model, just a 4-wheel cart. And this is a program structure. In order to use ROS, I designed several packages for this problem. The first part is a vehicle control part. So because this project is focusing on the sensing part, the depth sensing. So I'm using open loop control. So this part, vehicle control code accepts the input from the keyboard and send it to the gazebo. And the gazebo is a simulated robot environment. It can deal with, it has several physical engine. And it can deal with all the simulated part. And here is a vehicle description. It's the vehicle model where I'm giving the gazebo word. And gazebo word is the code to drive the gazebo to simulate the environment. And there is a simulated camera on the robot, and it will output image to another code. So it's depth estimation part. And depth estimation part will do the depth detection part for the task. And in order to do the triangulation, we need to get point for two consecutive images. And feature detection is done by using our feature extraction algorithm and the brute force algorithm provided by OpenCV library. And you can see these are the little circle in the image. The left part and right part are two different images. The camera captured at two different times, and the little circle on the image are the feature point, and they are obtained by using all feature extraction algorithm. And the next part is to matching those featuring point to each other, and we can get so we know this point after 1 second or several milliseconds it became here. And here is the process of the depth detection. The robot compares two consecutive images and finds the disparity of the feature points. Based on the trajectory of the robot calculates depth data through triangulation. So this part is simulation. Okay. So here is the gazebo world, and here is the vehicle control part, and I still need a depth estimation. Okay, so this is a depth information part, and if I'm trying to move the vehicle around, you can see that there are small white dots in this part. So they are actually the depth information detected by the algorithm, but you can see there are a lot of errors in that. The bigger the white dot is, it means the distance is very large. So a small white dot indicates the object is very close to the vehicle. So the results was shown just before, and you can see that although the robot can capture the depth information, the simulation results shows too much noise on the depth information. I think that the noise mainly came from the feature matching error. So during the time I was coding the featuring matching part, so a lot of points are just matching randomly. So there are a lot of noise in the feature matching part, and existing feature matching algorithm are mainly designed for matching static images, so they cannot capture the movement of the image very well. So I think that's this is the next part I'm going to try. So I'm trying to improve the matching algorithm and see if I can get a better result on this part, on this project. And that's all. Thank you.
Okay, good work. This is a very hard problem and very practical, relevant problem. So, what was? Are you using some kind of estimation technique here? Like, I know feature matching and all is going in the background, but are you just triangulating, or are you also using a Kalman filter to get rid of or to the errors or noise?
I wasn't using any like Kalman filter technique, but I think I will add them later. So at this step, I'm only using two consecutive images to calculate the depth information. So maybe I can.
So I think putting a filter will get rid of some of the anomalies or get rid of any bad data or bad matching. So it might help if you use some kind of filtering technique to continuously detect distances from the objects. But yeah, this is good work. Thank you. Any questions from the audience?
Yeah,
This gazebo world thing is pretty good.
I have a question. So what's the time interval between any two consecutive images, and how sensitive your results are based on that as a function of that time?
I was setting the camera frame rate to be 10 Hertz. So every two consecutive images are received at 100 millisecond interval.
So you just kept it at constant 100 milliseconds. You didn't kind of do an analysis of any variation of that time period, correct?
Yeah, I did try to set the time interval to be very small, but the error seemed to be very large if the time step to be error. You know, the trajectory will be very small.
That there is a minimum time needed, because otherwise the two images will be same, correct? So there is a minimum time that is needed between any two images, but it shouldn't be like too long. So that's why I was more curious about what's that sweet spot, that window of time between. Yeah. You answered my question. Yeah, thanks.
Yeah, that's a great question. And also, like, so millisecond means would a real camera give you this kind of frames per second, right? Like general cameras are 30 frames per second, or so will that?
Yeah, a normal camera gives the image much faster, but in the program, in the simulated environment, if I was using a very fast camera, then the results showed very different. It actually didn't. The program can actually didn't get any results because the distance is like to be infinite and sometimes zero. So the error will be will blowing up very quickly. So if the frame rate are very fast.
Great. I think this is a good initial. Yeah, go ahead, Sim.
Yeah, I have a question. Do you know the size of these spheres from beforehand? Because otherwise, how else are you assuming that how near or far these spheres are?
So the depth information are calculated based on a triangulation. So I will show you. So the robot can so imagine the black dot robot, and robot move to this place, and it see the same object here.
I can't see anything.
Oh, okay.
But Shoham, I think that's the objective, right? you don't know the size and all, but you are trying to estimate the depth. Why do we need size of the object?
Well,
it's the
because,
number of pixels tells.
Yes, the number of pixels needs to be mapped with the object, right? So, for example, if it is a building versus if it is a cycle stand pole, if there's no kind of feature separation as to what it is, then a building far away may as well look like a cycle stand, right? So it might have the same sort of shape and number of pixels that are being used up. So for a building, it
So
will
is
be
your question like, is he using any size information of objects to estimate depth? Are you, Leo?
No, I just using very simple feature matching algorithm, and
But you don't know the size of these objects beforehand, right?
yeah, the robot don't know the size of the object.
Okay.
Okay.
It's more like your algorithm doesn't require size information, is it?
Exactly. This is pretty cool stuff. I think this will be very useful if you are able to estimate depth using realistic frame speeds and use maybe some kind of estimation technique over that. Great. I think this kind of wraps up our presentation. So I will request all the judges to complete the form. So do all the judges have all the Microsoft forms that I created to evaluate every student project?
Yes, we do. We do have. Do you also send you're going to send the presentations, is it?
Yeah, I will send. So everyone, can you please submit your presentations as ASAP, and so that I can send the judges your presentations and they can complete the evaluation forms. And maybe in a day or two, I will get back with results. Okay. Right. Awesome. I thank all the judges, all the students. I request that all the students complete the naval evaluation that was sent by Karman. Please do that. It's very important for us. And also, so far only 7 students have completed the course evaluation, UC course evaluation. So I request everyone to complete that as well. And it will be great. Like it's like my grade, right? So like you guys get your grades, I need to get my grades and feedback to improve the class further. So it's important that everybody fill it out. And when we meet next time, we'll just grab a beer or pizza or something. Well, okay. Great. Thank you, everyone. Thanks, Krishna. Thanks, Rohit, Shoham, Anushka.
Thank you.
It's great. Yeah, it's a pleasure to be here. Yeah.
Yep. Thank you.
Thank you.
Thank you.
I'll put this on YouTube. Yeah.
Okay.
Here's the link with everyone. Bye.
Bye.